Hello, everyone. My name is Johnny Vu, and we'll be going over gradient descent, which is pretty much an extension of what we went over last video, the neural network. Yeah, so to start off this presentation, we'll be going over a small recap on what the neural network is and how it works. And then later, we'll be going into how we can apply this to challenges in science, mainly in digital biology. So, how does the neural network work? Recap. The neural networks are inspired by the brain and consist of interconnected layers of neurons, in which each of those neurons hold a number between 0 and 1, representing its activation. We can think of it as a light that's either on or off, or somewhere in between. The network begins with the input layer, like the 784 neurons representing a 28 by 28 pixel image. Each of those pixels have a grayscale value of 0 to 1, depending on how white it is. The final layer consists of 10 neurons, each representing a digit from 0 to 9, indicating how much the system thinks the image corresponds to a given digit. In between are hidden layers that handle the complex process of recognizing digits. In this network, there are two hidden layers with 16 neurons each. Activations in one layer determine the activations in the next layer, loosely analogous to how biological neurons fire. Weights are associated to connections between neurons, and a weighted sum of activations is computed according to these weights. Think of these weights like dials or knobs. This sum is then passed through a function like the sigmoid function or ReLU function to produce an output between 0 and 1, in which ReLU seems to be a lot easier to train than sigmoid functions. To represent these connections in a compact way, we organize all of the connections from one layer into a column as a vector. Then organize all of the weights as a matrix where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. This makes the relevant code both a lot simpler and a lot faster. The goal is to have the network learn from training data by adjusting its weight and biases. This is achieved through a process called gradient descent. Initially, the weights and biases are set randomly, resulting in poor performance. This is where a cost function comes in. A cost function is defined to measure the difference between the network's output and the desired output. It tells the computer pretty much how bad or how good it's doing. The average cost over all the training examples is measured of how poorly the network is performing. Gradient descent involves finding the minimum of the cost function. Imagine a function with many inputs, the weights and biases, and one input, the cost. The gradient of the cost function points in the direction of the steepest increase. By taking the negative of this gradient, we can step downhill towards a local minimum. This process is repeated iteratively, adjusting weights and biases to minimize the cost function. Each component of the negative gradient tells us whether the corresponding component of the input vector should be nudged up or down. The relative magnitudes of all these components tells you which changes matter more. An adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to some other weight. Some of these connections just matter more for our training data. Now we can see a real world application in the form of AlphaFold. Demis Hassabis, CEO of Google DeepMind, started his journey to AI with games like chess. Games provided a perfect proving ground for AI due to the ease of generating data and specifying clear objectives. This led to the development of AlphaGo, which mastered the game of Go through self learning. AlphaGo came up with new creative strategies and ideas that had never been seen before, even though we've played Go for thousands of years. This breakthrough paved way for tackling real world problems, with protein folding being a primary goal. The normal way to find the structure of protein is doing it experimentally, which can take months or years of work to determine the structure of even a single protein. For a typical size protein, there may be up to 10 to the power of 300 possible conformations that a protein
Proteins
can
are
take.
essential for almost all biological processes. Determining their 3D structure is critical for understanding disease and accelerating drug discovery. The protein folding problem involves predicting a protein's 3D structure from its amino acid sequence. AlphaFold 2 achieved atomic accuracy in predicting protein structures, incorporating evolutionary and physical constraints with machine learning. It has accelerated progress in tackling plastic pollution, neglected diseases, and fundamental structural biology. The latest version, AlphaFold 3, models interactions between proteins, RNA, DNA, and ligands, which is a major step towards drug discovery.
Biology is incredibly dynamic, and all the interesting things happen in biology when different aspects of biology interact with each other. With AlphaFold 2, you can think of it as solving a static picture of a protein, while AlphaFold 3 is our first step towards model interactions and the dynamics. By looking ahead, we can see that AI offers a new approach to solving problems by finding optimal solutions in vast combinatorial search spaces. This involves learning a model of the environment from the data or simulation and using that model to guide a search process. This approach can be applied to chemical compound design, leading to a new era of digital biology. Hassabis envisions simulating an entire virtual cell to revolutionize drug discovery, potentially reducing the process from years to weeks. Hassabis proposes that any pattern or structure found in nature can be efficiently discovered and modeled by classical learning algorithms. DeepMind is applying these AI techniques across various scientific fields, including medicine, climate, and mathematics. This includes medical image analysis, genetic sequence analysis, controlling fusion reactors, weather predictions, and discovering new materials. In a quote said by Demis Hassabis, AI is a dual purpose technology and it must be built responsibly and safely to be used for the benefit of everyone. So, what could we learn from all this? In conclusion, AI has the potential to transform our understanding of how the world works. However, it is very important to develop AI responsibility, making sure it benefits everyone. Depending on how we develop this AI, it could change the course of our future forever, for the good or bad. A technology as transformative as AGI will require exceptional care and foresight in order for it to steer us to the next stages of development of this incredible and powerful technology. Thank you.